Okay, let's get started. I'm Minje, the TA of this class, Programming for AI. And can you hear me now? Well, cool. And wait a sec, bro. Yeah, cool. And today I'm gonna proceed the practice session on autoencoder and plus denoising autoencoder, one of the variants of autoencoder. And oh, there is a chat. Okay. And you should in this session you just call the library, set the hyperparameters and data set and data loader, and modeling and defining loss function and optimizer, and training the model you defined, and that's all. And after the training of the model, you have to check what did you do with the t-SNE algorithm, like this. And for the denoising autoencoder, you have to do same thing as before. That's all. And I will give you 15 minutes. I will give you 15 minutes for each session. I mean the autoencoder and both autoencoder and denoising autoencoder. And is there if there is any question, feel free to write. Okay. Here. Oh, for a sec. Maybe. Does the attendance sheet work well? 출석 체크 명부가 잘 작동을 하나요? 네. 그 다시 공유를 하겠습니다. Okay, then if you have any questions, feel free to chat your question on the chat box. And let's get started. First, you have to required library. You have to import required libraries like NumPy, Torch, Torch.neural network, Torch.optimizer, Torch vision and datasets, transforms, data loader, and matplotlib, Python plot to visualize what you made. And you have to set the hyperparameters like batch size and learning rate and number of epochs. I think the TA Kyungun already covered this kind of things, and let's move on. And you should download the data, MNIST data. Today we're gonna use the MNIST data for our practice session, and you have to download. It is already split, like train and tested and valid. And you just simply put the Control plus Enter and running this, and like this. Not Control plus Enter. Shift plus Enter. And is there anybody know that what this size means? you already download the data from the server, and in this object, dataset object, there are several internal methods like this and properties, and through this get item function, you can approach each data. Oh my, no, my bad, like this. And it has a tuple shape. You can see this parenthesis, right? There in this tuple, there are two elements in it, and the first element is this tensor, and second one is label for the tensor, right? And if you want to get, oh, somebody already answered it, right? Channel and height and width, because MNIST is basically black, gray, white data, like as you look like this, and you, if it is a lot of, for example, the like data sets IFR10, it consists of 3 channels, are red and blue, red, blue, and green, but this is only just white black image. So you have the MNIST data has one channel, a single channel. So as Hangul and Wonjong said, it means channel and height and width. And you can approach, you can refer the size of the torch tensor and the corresponding label, right? And initialize the empty dictionary, and by running this cell, you get the 3 elements in it. I mean, in the dictionary you already defined, and each one means the data loader for train, valid, and test set respectively. And let's do the modeling. Let's model the autoencoder. You can just fill the blank, like there are several question marks block like this, and I will give you the 15 minutes for completing this question marks. Yeah, you get the 15 minutes for each. I mean, the autoencoder and denoising autoencoder. So you have to do the fill the blank until what, 11 a.m. right? Let's go. And if you have any question, feel free to reach me. And you don't have to do the denoising autoencoder now. For now, I will give you another 15 minutes for the denoising autoencoder. Okay. Oh, this is solution. And Okay, it's 11 a.m. and is there anybody who needs more time? Yeah. Okay, maybe nobody asked. So you all guys maybe are familiar with this stuff. But let's go. In my case, to be more specific, I want to put an emphasis on the channel. Okay. If you wanna tell me something privately, and just feel free to send a DM, direct message to me, and or the original input space is like 784 dimensional vector, and I want to compress it to 30 dimensional vector and decode it back to the original space. And I did it with the linear layer, and my choice of activation function is value, but you can freely choose convolution neural network to encode and decode this vector or tensor, and you can choose another activation function rather than value, like Ricky value, sigmoid, or something. But what you should know is, maybe you notice the characteristic of this data set. What do you think of this sigmoid? You think why did I put the sigmoid function on the last activation function? Anybody knows? Right. Oh. As Seungmin and Dongsu said, the all of elements of this tensor in the MNIST dataset is smaller and inclusively smaller than 1. So you have the output space should be restricted in the interval from 0 to 1. That's why I put the sigma function on to this last layer. And look at the fourth function, internal methods fourth function. You get the batch size and flatten by view function, flatten the vector input vector by view function, and encode the input vector with this self.encoder, and decode it back to original input space with self.decoder you defined, and deflatten, reshape the output vector like the original input. That's all. the output of this autoencoder model is out variable, which is defined one line above, and encoded, which is a latent vector. And you set the, yeah, these are already built, and you set the loss function and define the, is running this after running this cell. Yep. Question. Oh, but you question like this. With Sungir's question, what is the difference between view and reshape functions? And Sungir wrote the message, direct message to me, but I think it is quite, it could be public, so, and quite good question. So I wanna you guys to know this. And what is the difference between view and reshape function? Actually, it works as like, for example, or like, that's all right. The shape of this tensor is 32 by 32, and Singer's question is like, what's the difference between this and this, right? Oh, I didn't. Let me initialize like this. This is Singer's question. What is the difference between view and reshape? Anybody knows? Also, Eugene threw the question like, why did you consider batch size for flattened vectors? And it's quite academic. Oh, hey guys, please, if you feel your question is quite academic and helpful, be helpful to what other classmates, just don't, you rather text text the chat to everyone, not to only me. There are several questions already. First question is like this, and second one is this. Why don't you consider batch size for flattening vectors? And second one, the third one is, could you explain the reshaping process in which the dimension of the tensor changes after decoding? Why the output tensor should have the batch size in their tensor form? As I know, the two function view and reshape work similarly, but the difference whether the function can be applied to it works, as Hunter said, it works similarly, because as you can see, like Some sums are omitted, so I will reinitialize the vector A, and let's do the view and reshape function. And the content is totally the same, but the difference between view and reshape method is like allocating memory issue. As Hanger said, but the difference is whether the function can be applied to contiguous equal true tensors. Contiguous means like some memory, each element of the tensor will be allocated into computer memory, I mean. And contiguous means the memory, the address of memory is right next to other one. Like this, if the index of the memory is like this, then it is contiguous. But like this is not contiguous, as I know. From my understanding, this is the difference, because it is not. 2 is right next. If the 2 is right next to the next memory to the 1, first memory space, it is contiguous. But the other case, the second one is like 1, 3, 5, 7, and there are empty space like 2 and 4 and 6. They are not standing in a row, right? So there are empty space like 2, 4, 6, and this is not contiguous and different. And this is difference between the reshape function and view function. And I think you're already good at English, Hanger. And second one, why don't you consider a batch size for a flattened vector? You mean this one, Eugene? Okay. Okay, then again, MNIST train. You got a sample from MNIST train data set, right? And your question is, if this is X, and if you, so Eugene's question is, why, where is it? I didn't consider the batch size for the flattened vector, which is, maybe she thinks like, like this. In this case, the batch size is, the batch consists of a single element, single data points. So maybe she thought that this is more a kind of the better form of better form to use the view method, right? If you put the element like this, then you can get the batch size, of which shape of batch size and one channel 1, and 28 by 28. Thank you, I understand. But you already got it. But let me continue to answer it. The linear function only attends to, it works only for example, if you view like this, as you said, it has shape 1,1 as 1,1, 784, and how about this? It only attends to the last dimension of the tensor, so you don't have to consider the batch size. When you flatten, when you're at the early stage of encoding, like flattening input vector. So anyway, what I want to say is, the point is, the linear function or linear layer only attends to this last element, like 784. So you don't have to consider the batch size at the early stage of autoencoder. So that's my answer. And Jie Tang, please forgive me. I'm not a multi-linguistic person. Yeah. Why is there a batch size in the view operation of the second last row in definition forward? And let me briefly cover could you explain the reshaping process? Let me cover first. Let me cover the question of Woo-jung first. Could you explain the reshaping process in which the dimension of the tensor changes after decoding? Could you explain the reshaping process? Why the output tensor should have batch size in there? Maybe this question is like Jie Tang's question. So you're curious about this. As I said, the linear layer in the encoder and decoder only work with corresponding last dimension, as I said. For example, there is and if you want to view if n and the linear, the first argument of n and the linear, the input dimension is same as the last dimension of the input vector, like this. This is X shape. And if this last dimension is same as linear, then it works. The linear works, regardless of the extra elements, right? And that's the answer for Eugene and other guys. And your question is like, why do I have to consider batch size? Like, this with this view function. And I will explain it. I just picked a what's X? I already deleted. Wait a sec. Used data set. Oh. And you have to reshape to, this is original shape of tensor, and you have to view this tensor into this. But your question is, why batch size matters here? 나 지금 저거 봐봐. 저게 안 yeah, let me continue. It, as I said, it works with the linear layer, only works with the last dimension, but as you collapse this, because you collapse the in the data, when you load the data as when you load the batch-wise data, data loader works like the output of data loader is like this. So you have to, and your model should work in a batch-wise way. I mean, your input X will have a shape like batch comma, channel comma, width and height. So you have to care, unlike the linear case. In the linear phase, when you encode and decode the tensor, this will, let me give you a pseudocode. This shape, the shape of tensor will be like this. So you have to separate like batch -1, separate each dimension like this to decode it back to original input space. You guys understand? You're not gonna treat the single data points. You're gonna do that. You're gonna train and validate the model with batch-wise operation, batch-wise operation. Yeah. So that's why I put the batch size here, and you already asked this batch size. Why should this batch size variable exist? And I will ask you again. We already set the batch size as 256, right? So maybe you don't have to refer X because batch size is already predefined, right? So if you want to do that without And you can do like this and fixed. You can use fixed. Oh shit. Sorry. Self dot batch size. And you can do like this instead of call the batch size each time. But why did I call the x dot size 0 every time? You know what I mean? You know, instead of this line, you can put the self dot batch size, and you can use the fixed batch size like 256 like this. But why? Why didn't I do this? That's my question. Is it okay? Is it okay to use fixed batch size like 256? Anybody got an idea? Then the model wouldn't work in other data format. But if I use this one, I don't know what I mean. We can handle batch size easily. What do you mean by we can handle batch size? So you mean by putting this line into this for function, I can handle the batch size easily. That could be one of the reasons. But what Ujung said is what I want, what I originally intended to. The size of the last batch is possibly different. Yeah, that's right. Last batch size may not fix with 256 there. Yeah, that's also right. So to put more explanation on it, if there are 256, I don't know, it will be confusing. If there are 32 data set, 32 data in the length of data set is 32, which means there are 32 data points in the data set in total, and your batch size is 8, and you can clearly, it consists of 4 batches, right? Batch size. But how about, this is case 1, but how about this case? No, 5, 6, and 6, and how can I don't know the mathematical notation. 2. There are extra portion of 32, right? If you divide 32 by if you divide the 32 by batch size 5, then you can get another extra 2. So if you use the fixed batch size like 5, then this one will output the error message on what tensor shape blah blah. you are not going well with your tensor shape. Yeah. So to prevent this error message, I call the shape of x tensor x at each time step. Okay, let's move on. It's already 11:30. I'm sorry to fail to manage the time. And let me just, yeah, or you guys already trained the model, right? But I have to train now. Ooh. Okay, after this training process, I will plot the train loss history, and validation loss history. And the graph consists of X label with epoch versus Y label with loss. And with plt.show method, you can visualize how the model works in the training phase. And you can check whether if the model fall in the overfitting. It doesn't look like it. It doesn't show overfitting, right? So the conclusion, the small insight from this figure is like it's like 9 epoch is not enough to train completely this model, right? Yes, I like to see that too. Can you share your train code? This one? You mean this one? Well, by the way, I will share the solution code, not with the code, not with this blank. I will share the solution code on the classroom, so you don't have to worry about it. Yeah. And check with the test image. You can run. And this is original data 1, 2, 3, 4, 5. And this is reconstructed image of 1 and 2 and 3, 4 and 5. And with your model, you encode this image one to into latent vector, small latent vector with where is it? 30-dimensional space, and decode it back to original input space. And this is the result. And to visualize this MNIST data, I used t-SNE algorithm, and there is no question marks here. And you can just run it to visualize what you made. Yeah. As you can see, as I already said, the model outputs 2 elements. One is the tensor for original input space, and second one is latent vector. And second latent vector would be used in this part, this t-SNE part, visualization part. And you can visualize the latent vector. Okay. And there are 10 categories in the MNIST data set. I mean, the 0 to 9. And this is divided by 10 sections. It consists of 10 sections corresponding each class of MNIST data set. That's all. You can also use PCA, but it may not classify each class. It doesn't separate each class. So t-SNE would be better choice to visualize the latent space. And it's 35. Yeah. Denoising autoencoder. I will give you 5 minutes for denoising autoencoder. Because originally I wanted to give you 15 minutes for the denoising autoencoder part, but what you have to do, what you only have to do is adding noise function. That's all. That's the only difference between only difference of training model D function between denoising autoencoder and autoencoder. So you have to initialize the noise from the standard normal distribution and add the noise to the original input, and decode it back to original input space. That's all. And as I already said, the only difference is adding noise part, as I wrote like this. It's all the same except for one, adding noise into inputs. So it will be easy. And let's meet again at 11:40 a.m. And if you have any question, feel free to reach me. Go. Let me share the training code now. Oh, not this one. Not that I mean the training code for autoencoder, not the denoising autoencoder. Oh. Some guys need this code to proceed denoising autoencoder parts. So this is training model function for autoencoder, and you can really refer this code, the completed code, and just add the just add the code for adding noise yourself. Please fill the blank with this code in the autoencoder part. We haven't filled question marks on the train model, so we can't copy the code for denoising section in the first place. That's why I show you this code now. This is code for autoencoder, and this is whole training code for autoencoder, and you can just add some lines of code for adding noise. Yeah, this is solution. Cool. Can you guys look at it well? I think it is way too small. Oh shit. How can I? We can only refer this part. Okay, it's 11:41, and is there anybody who needs more time for completing the denoising autoencoder part? You can DM to me. Um, okay, zoom in. You want this part, right? And page this one. I can zoom in this. Okay. Is it okay? Maybe there are several students who needs more time. Can I move on? No? As I already said, you can download the solution code from Classroom soon. Okay, let's move on. Oh, some guy said, I cannot do forward function due to not all tensor is one same device. Maybe you do something wrong. You did something wrong with the two CUDA code or something. Two device code, like here. You have to set the device like this. And yeah, you have to care about it. Okay, let's move on. The only difference is like this noise part. You have to initialize the noise with normal distribution, and you have to put the noise into device you already set, and this input you would do the operation between noise and this noise and input, so these should be on the same device, and that's kind of error you faced now, maybe because you have to output this noise input by adding inputs to the noise, and this is operation between the two tensor, and that two tensors should be on the same device. That's all I want to say. And this is only difference between autoencoder and denoising autoencoder part, and you can simply training this one. Not training now. You can define this one and start it to train with 9 epochs Wait a second, please. Is there any question that I didn't answer yet? Um, maybe I already answered all the questions you guys asked. And as you can see, after the training, you can visualize the training process with the loss curve. And as you can see, and same as before, valid loss curve for validation is still decreasing, right? There are some margin to proceed. So what it means, I want to say what it means. It shows that the model is not trained enough yet, and you have to increase the number of epoch, and by doing so, you can train it enough. And with Perch Nograd, you can validate the model with test data set, and you don't have to operate, you don't have to calculate the gradient for test data set and validation. So with this decorator code line, we can deter the complicated computation process. So this is the output of the denoising autoencoder. What's the difference between autoencoder and denoising autoencoder? By adding, as you add the noise to input with a single line of code, several lines of code like this, you get the noised input, corrupted images, but you're denoising autoencoder, as its name already said, denoise the image, like this one decoded this region with corrupted image is decoded back to black one. So your model, not your model, but my model completely denoised the corrupted part. And it seems the character, this number is clear to discriminate the 1, 2, 3, 4, 5. So my denoising encoder works well, as you can see. But how about yours? Yours doing well? Yours are doing well? This is in original case, in original autoencoder, this remaining part is like black one, a noised one now. And maybe your denoising autoencoder works well like mine. So this is the end of the practice session. And is there any question? Feel free to reach me. My email address is, oh, This is my email address, and feel free to reach me by email or any other things. And if there is no question, I will end the practice session. Yeah. Thank you all, guys. See you later. Bye bye.
감사합니다.
Sure.